Okay, what questions do you have? You just said you had questions. E1 and SN1, the differences between them. Okay. What else? Let's start with that. So E1. So E1 and SN1 share the first step in the mechanism is common. So let's say that I had this molecule. So I'm going to take this, which is terpenenyl bromide. And whether this was SN1 or E1, what would the first step in this mechanism be? Break the CBr bond. So I break the carbon-bromine bond, and I would end up with the carbocation. And that is the rate determining step for either SN1 or E1. Now, where SN1 and E1 are different is, let's say that I don't have a nucleophile present that can add to that carbocation. There isn't a nucleophile there, and so therefore it can't be SN1. Well, what can happen is that I can lose an H plus to form a double bond. So E stands for elimination. And any elimination reaction is always going to form a carbon-carbon double bond. This is just going to be unimolecular elimination, meaning the kinetics are unimolecular, meaning that this is the rate determining step. Now, in order for us to form a double bond, we're going to have to lose an H plus. And in order to lose the H plus, we need to know, well, what hydrogens can we lose? And the terminology that we use here is that the carbon that's attached to the leaving group is the alpha carbon. That is always called the alpha carbon. And then what are attached to alpha carbons? Beta carbons are attached to alpha carbons. And the hydrogens attached to the beta carbons are beta hydrogens. So we can write the product of an E1 reaction without going through the mechanism, but we will go through the mechanism. Okay, but we need to understand that terminology. So alpha carbon is the carbon with the leaving group over here. That becomes the carbocation, and then there are three beta carbons next, or that are attached to that alpha carbon. So what I want to do is I want to write out those CH bonds explicitly here for the beta hydrogens. So alpha carbon, beta carbon, beta carbon, beta carbon, and then this would be a beta hydrogen, this would be a beta hydrogen, and that one would be a beta hydrogen. So those are the hydrogens that can be lost to form the double bond. And the way that they're going to get lost is that, for instance, if let's call this beta hydrogen 1 right there. If I lose that H plus and take its pair of electrons and have that carbon donated to form the double bond, what happens is that I lose H beta hydrogen 1 plus. So I lose it as an H plus. The same way that we were losing H plus when it was attached to water or an alcohol when we were doing the SN1 reactions. Only this time I'm going to lose it as it's attached to the carbon. And then that carbon's going to take that lone pair and use it to form the carbon-carbon bond, which is going to get rid of the carbocation. And so when I do that, I'm going to end up with the double bond there to that carbon. And so I'm going to form a double bond between those two carbons. And what we always do is we always form a double bond between the carbon, alpha carbon, and the beta carbon. That's how it always is formed. Okay. So this is one of the possible products if I was to lose hydrogen 1, beta hydrogen 1. Is everybody with me? Because if you're not, you gotta say something. So that would be one possible product. The second possible product would be to lose beta hydrogen, let's call it 2, by the same mechanism. So I'll put this one in red. So beta hydrogen 2 here, I'm going to take this pair of electrons and I'm going to move it, again, losing H plus, but then having that carbon have the ability to form a double bond with the alpha carbon. And so that product is going to have a C double bond CH2, over here CH3, over here the CH2 CH3. So this would be my product if I lost beta hydrogen 2 plus. So I'm going to lose that H plus, and I'm going to get that product. And again, if you're thinking about what is my final answer has the double bond between the alpha and the beta carbon. Up here it had the double bond between that alpha and that beta carbon. So I'm always forming a double bond between alpha and beta carbons. The other carbons would be the gamma delta carbons. They don't come into play. You only form a double bond between alpha and beta. Okay. So if we take a look at these two possible products, my first question is, are they the same product or are they different products? And in order for them to be the same, they would have to have the same IUPAC name, and they have to have the same structure. Now, if you've forgotten how to IUPAC name alkenes, you could always look at this and say, well, let's see, I've got a CH2 here, double bonded to a carbon with an ethyl and a methyl. CH2 here, carbon double bonded to a carbon with a methyl and an ethyl. So it seems like they have the same structure. And there's no cis-trans easy possibility here, because this carbon with its 2 hydrogens can't be cis-trans or easy. So structurally they seem like they're the same. And that's because they are the same. Looking at the IUPAC name, this would be a 1, 2, 3, 4. So this would be a 2-methyl but 1-ene would be its name. And you may have seen me use the older terminology by calling it a 1-butene maybe in the videos. Those were prior to top hat. Okay, so this one, we would start numbering the longest chain closest to a double bond. This would also be 2-methyl but 1-ene. So they have the same IUPAC name. They are the same molecule. So whether I lose beta hydrogen 1 or beta hydrogen 2, I'm going to end up with the same product. So this is the first possible product of E1, is this one. Everybody with me? Do I not need to go over this? So let's get the other product done. So carbocation, I'm just going to put my CH3s because now what I'm going to do is now I'm going to lose a hydrogen off of, well, this beta carbon. Let's call this beta hydrogen 3 over here. Okay, and so I'm going to move this pair of electrons here to form the double bond. I'm going to lose my H+, so I'm going to lose an H+, a beta H plus 3, and now I'm going to end up forming the double bond between the alpha carbon and the beta carbon that was on the right. So I formed 3 products by forming a double bond between the alpha carbon and each of the beta carbons. It just so happened that the beta CH3 group to the left and the CH3 group that's down produce the same product. And so this a new product. I would number this longest chain and closest to the double bond. There's a tie there, so I have to go with the one that's closest to the methyl. So now this would be 2-methyl but 2-ene. Different name, different molecule. So these are the possible products of that reaction. The possible products are the 2-methyl but 2-ene, and then having the CH2 double bonded to the 2-methyl but 1-ene. So those are the 2 possible products. There's 2 ways to get 2-methyl but 1-ene. So everybody okay to this point in terms of the mechanism? So then the question becomes, this is our first reaction where we've had more than one possible product. And whenever we have a reaction that gives us more than one possible product, we have to ask ourselves, what's the major product? The major product being the highest percentage product. If there's just 2, it could be 51-49. If there's just 2, that's going to be a majority. Anything above 50. If there's 3 or more products, it's whatever the higher percentage. So what's the major product of this reaction? And there always has to be rules for this. So each reaction is going to have its own set of rules. Bless you. So in this case, the rule is that you form the double bond that is the most stable. Okay, so that's the rule. The rule is that in an E1 mechanism, you form the most stable product. And that product is an alkene. that is also called the Zaitsev rule. And Zaitsev is spelled in a bunch of different ways because Zaitsev was Russian. It got translated into German, which got translated into English. So there are many different spellings of Zaitsev. And what Zaitsev did was, Zaitsev did a bunch of E1 reactions. He didn't really know they were E1 reactions at the time. And I'll show you the specific reaction he did because it wasn't this one. It wasn't with alkyl halides. But he did these reactions and he found out that he always got the most stable product. Although he didn't know it was the most stable product at the time. And so that's why we call it the Zaitsev rule. I have not looked at the original Zaitsev paper to make sure that that's actually what he did. We'll talk in a couple weeks about Markovnikov, and Markovnikov didn't do anything like what they give him credit for. So it could be Zaitsev just gets credit for this, even though he didn't do it, but it sounds better that he did. But all he did was just say, every time I do this reaction, this is the product I get, this is the major product. And then it took probably 50 or 60 years to figure that out, why. So what is the most stable product? Well, in order to understand the most stable product, we need to look at a carbon-carbon double bond. And what would make a carbon-carbon double bond more stable? Carbon-carbon double bonds tend to like electrons to be pushed into them. The more you can push electrons into a double bond, the more stable you will make it. So we go back to our alkyl groups. We go back to the alkyl groups and we say, well, what would happen if I put an alkyl group on the double bond? The hydrogens would be slightly positive, the carbon would be slightly negative. Every time I put an alkyl group on a double bond, the alkyl group has the ability then to push electron density into the double bond. The double bond likes that, and it becomes more stable. So we are back to where we were with carbocations. The more stable the carbocation, the more alkyl groups were attached to it. The same thing is true for the double bond. The more alkyl groups you attach to a double bond, the more stable it becomes. And so that's the reasoning for why Zaitsev's rule works the way that it does, is because you form the more stable product, and the more stable product is the double bond with the most number of alkyl groups attached to it. So in this case, does that make sense? Yeah, well, we need to test that out, that it makes sense. So here's product A and here's product B. Tell me which one of those two is the more stable product, which means it is the more substituted product. With your cards. And if you need a card, I've got an extra card. I've got more extra cards if you need them. Okay. Which one is more... Which one's more stable? A, B, or we could put in C that means they have the same stability. Which one is more stable? Okay. We have 14 A's and we have 7 B's. Okay. Not bad, 2-to-1, if it's in the right direction, meaning A is the major product. So let me ask the question then. Let me rewrite these structures over here. So there was product A. And here's product B. How many alkyl groups are attached to the double bond in product A? Okay, and your choices are 1, 2, 3, and 4. So how many alkyl groups are attached to the carbon-carbon double bond in A? One, two, three, or 4. Okay, we've got 2 1s, 2 2s, 17 3s, and 1 4. How about B? How many alkyl groups are attached to carbon B, or to the double bond in molecule B? We've got 23B, 23 number 2s, and 1 4. Okay. All right, so counting. A carbon-carbon double bond can have up to 4 things attached to it. And so the question is, how many of those are alkyl groups? So in A, it's 1, 2, and 3. So there's 3 alkyl groups attached to the double bond in molecule A. Over here in B, there's 1, 2, so there's just 2. Now, when you first start with this, sometimes it's easier to count hydrogens than it is to count carbons. And if you count hydrogens, then you're just going to take 4 minus the number of hydrogens, will give you the number of alkyl groups. So for instance here, there's just a single hydrogen, 4 minus 1 would give me 3 alkyl groups. Over here, I've got 2 hydrogens, 4 minus 2 would give me 2 alkyl groups. So whichever way you want to do it, you need to count the number of alkyl groups. In this case, A has 3 alkyl groups, B has 2. That would make A the major product of the reaction with the double bond with 2 methyl groups, then the double bond to the carbon with an ethyl and a hydrogen. Okay. So A would be the major product of that E1 reaction. Does that, any questions? Okay, then let's go to rings. Because usually people will be, I'm fine without the rings for some reason, just confuse me. So my question here is, how many unique products are there? So if 2 products are the same, they only count once. So how many products do we have for this reaction, and what is the major product? There you go. Then I'll ask you for the products, and then we'll vote on the major one. So you can do this either way. You can either start the mechanism, or you could identify the alpha and the beta carbons. If a beta carbon has a beta hydrogen, then that's what the double bond could form, if you want to just write your products that way. Really, all your muscle products are going to be bringing alpha and beta carbon. So if you can identify your alpha and your beta carbon, and your beta carbon has a hydrogen and blues, you can form a double bond.
Structures of each other, and you major structure.
Okay, so then the question is, are any of those the same? The question is, any of those the same? Which one's the major product?
But there's only two.
This would be a beta carbon for these
So then the next question is, are any of those the same? And then the second question is, which one's the major product? I wouldn't think about that. I'll buy the first one, but so you know about the second one.
I said that this would be the major product.
Okay, so if we're looking at this molecule, this is my alpha carbon. How many beta carbons do I have? I got 1, 2, 3 beta carbons. Now, whenever you're looking at beta carbons, you need to see whether or not they have hydrogens attached. Because if a beta carbon doesn't have any hydrogens attached, you can't form the double bond to that carbon. Well, you can, but in the end you'll have 5 bonds to that carbon. Okay, so if we're doing this by mechanism, we would break the carbon-chlorine bond, and I would form a carbocation here. Then I'm going to have a CH2 with an H. I'm going to have this C with an H here, this C with an H here. I know that those 2 carbons have two different hydrogens, but if you lose either one of them, you get the same double bond. So I could lose this hydrogen, I could lose this hydrogen, or I could lose that hydrogen, which basically means that I can form a double bond here to the top one, a double bond here to the bottom one, and a double bond outside of the ring. So those would be my 3 possible products. Would be A and B and C. So I'm going to form a double bond between the alpha and the beta carbons. The critical part is that the beta carbon must have a hydrogen that can be lost. Is that what people had? Any of those 2 the same? Or I should say, any of those the same? Are they the same molecule? Which ones? A and B? So A and B are the same? Okay. They're the same product because basically they have the same name. They would be 1-methyl-cyclohexene. C would not be 1-methyl-cyclohexene. If I wanted to name C, I'm going to need to get my chart out because C is not one that we named. We did a lot of naming, but we didn't name those. So we'll just call it not 1-methyl-cyclohexene. Okay. So let's just call this one A and C. So of A and C, which one's the major product? A or C? You can have D if they have the same. So which one is going to be the major product, the most stable alkene? A, C, or if they're both the same, D. If they have the same stability. A or C, and D if they're the same. Okay. What happened? All right, we've got 15 A's, 1 B, which is an A, 4 C's, and 4 D's, which they have the same energy. Okay. Well, my next question is going to be, looking at A here, how many alkyl groups are attached to that double bond? Your choices are 1, 2, 3, or 4. We're going to do this for A and for C. Let's start with A. For A, how many alkyl groups are attached to A's to the double bond in molecule A, or the molecule in B? They should be the same number. 1, 2, 3, or 4. A through D. Okay. We've got 5 A's, 8 2's, and 11 3's. I think you might need to discuss for a minute. For A, how many alkyl groups are attached to A? Discuss. And then we'll revote. Okay, we ready to revote? Let's revote on the number of alkyl groups attached to the double bond in carbon A. 1, 2, 3, or 4, A through D. So how many alkyl groups are attached to carbon A? Or to product A? The double bond in product A. We've got 21. We now have 21 threes, a couple of 2's, and a couple of 1's. Okay. So how many alkyl groups are there? There's 3. Let me put in the hydrogen. Okay, so rings are sometimes easier initially to do by counting hydrogens and counting carbons. So in this case, attached to that double bond, there is 1 hydrogen. So that means there needs to be 3 alkyl groups. Where are those 3 alkyl groups? Carbon 1, carbon 2, carbon 3. So those are the 3 carbons that are attached to this carbon-carbon double bond. So that would give us a total of 3. Okay. Without being able to count the number of carbons attached to the double bond, you're going to have a more difficult time figuring out the major and minor products. Okay, let's just for fun, let's go to C and tell me how many alkyl groups are attached to the double bond in molecule C. 1, 2, 3, or 4. Okay, we've got, over here I've got 2 1's, 18 2's, 5 3's, and no 4's. So if you're not quite sure on this one, maybe what we should do is to take this CH2 over here, and maybe we should write it out like this. So how many hydrogens are attached to the double bond? 2. 4 minus 2 means there should be 2 alkyl groups. Where are they? They are here, and they are there. So this one just has 2 alkyl groups. This one over here had 3. So what's the major product? The major product should be A for an E1. For an E1, it's always the most substituted product. So that's going to be what we need to do. We need to be able to write the mechanism for E1. We need to be able to write the possible products for E1. And then we need to be able to determine what the major product is. Okay. Questions? Okay. I'm just thinking. There's been questions about, the book has introduced the idea of rearrangements. The last 7 minutes is probably not the best time to start rearrangements, although I could. No, I could. We could finish it up next time. But I don't think we're going to talk about rearrangements yet. What we'll do is we'll wait until after next Monday's exam, and then we'll talk about rearrangements. So, let's do another one of these. So here is another alkyl halide. I want it to undergo E1. Okay. So, what are the possible products of this reaction? So I'll give you 5 minutes-ish, and can you write out the products, the possible products? And then, of course, my ultimate answer, or my first part is what are the possible products? Second part, what's the major product or products? If there are ties, then there's going to be more than one possible product. Well, more than one major product. So what would be the products of those reactions? What would be the possible products here? And then we'll go from there. Okay. Okay, if we have these ones then. So if we have our alpha and our beta carbons, let me just show you without doing the mechanism how you could write the products directly without the mechanism. So we're going to lose HCl in this process. That's what the elimination is. So we're going to lose the beta hydrogen and the Cl. So if you think about just, I want to write the final products, if I lose HCl that way from that beta carbon, remember I'm always forming a double bond between the alpha and the beta carbon, so that would be like product A. Or I could lose the HCl on this side, so what I've done is I've now formed the double bond between the alpha and the beta carbons, and there were 2 beta carbons, so therefore there's 2 possible products, A and B. Okay. So if you don't go through the mechanism, this is a way to quickly write the products. You're just going to form the double bond between the alpha carbon, and what's critical is any beta carbon that has a hydrogen. If it doesn't have a hydrogen, cannot form a double bond there. Okay, so then if we have A and B here, which one is our major product? How many alkyl groups are attached to molecule A, to the double bond in molecule A? Give me a number. 3? Do we like 3? It looks like there's just 1 hydrogen, so there is 1, 2, 3 carbons, so that one has 3 alkyl groups attached to it. How about the double bond over here in product B? How many alkyl groups there? 3? Okay, so again, 1, 2, 3 with 1 hydrogen. They're tied. So what does that mean? They're both going to be the major product. So the major product of this reaction should be major products of this reaction, and that would be both A and B. So when we talked about carbocations, it doesn't matter how many alkyl groups are attached to a carbocation. 3 methyls are as good as 3 ethyls, which are as good as any combination. The critical part is the number of alkyl groups, not what they are. Same thing is true here. Any alkyl group stabilizes the double bond. Methyl, ethyl, propyl doesn't matter. Part of a ring doesn't matter, although our rules are just going to be count up the number of alkyl groups, and it doesn't matter what those alkyl groups are. Okay. Okay, so that's E1. E1 is a little more straightforward than some of the other ones, but the critical part is being able to write the products and then being able to do that. Now, here is your graded homework problem. I will put this online. What I would like you to do is to do the E1 mechanism. For that, again, I will put this online. I would like you to write the mechanism for this. I'd like you to show me the mechanism for forming in this case, 2 major products, including the transition states. So I will put this online after class, but that's going to be your practice problems for Wednesday. And I'm giving that to you because this is something that I might ask you to do next Monday on the exam. Okay, I will take your graded homework problems for today on the table. I will put this up. If you have any questions, ask Piazza or email or face-to-face.